So my name is Tuhin Malik. I am from University of Coimbra, Department of Physics. I am working in the group of Professor Constanza Providencia. We have worked in relativistic mean field models to infer the dense matter equation of state from a few minimal constraints. I'll describe in the next few slides. So if you look at the in the recent days, there are many good equation of states are already there, and they are very good in the sense to describe the US span in the compatible with recent observations. This kind of US basically at the low density region, it is constrained from chiral effective field theory calculations for pure Newton matter equation of state, and high density. You can see that the perturbative QCD at very high density, and intermediate regions, either it is polytropic fitted or maybe speed of sound interpolations. And there are many recent papers already to know about the what is the NS matter equation of state span or possible NS matter equation of state in light of recent observations. But we are trying to go one step further back, that if we know the equation of state, can we say about something about proton fraction at any given densities? And if we know the equation of state, can we say about anything or the chemical composition of the equation of state? So for that, first step, we did a first step calculation that in the nucleonic assumptions. First, we are going to see that what are the possible nucleonic domain of equation of state possible for compatible with recent observations, and also analyze the different individual component of the equation of state, either the symmetric nuclear matter equation of state, symmetry energies, and different NS matter properties, and understand that there are limitations of the high density, higher order nuclear matter parameters. Normally, Newton stars to get the structure equations, solve the structure equations, TOB equations, one need to have the equation of state. After solving, it will the TOB equation when we get the NS properties. And then now these properties and this US you will build up with some theoretical assumptions. Every theoretical assumptions has some parameters, and to fix the parameters or couplings of the theories, one has to change the couplings, and again it will go to the in the flow of give rise to different NS properties. Now we can optimize these parameters to get the proper couplings or something. There are two approaches. One is frequentist approach, another is Bayesian approach. So nowadays, familiar one is you can say the Bayesian approach. So it is little bit computationally costly, but you will get the complete picture of the parameter space. In the frequentist approach, you fix the minimize the chi-square. It may possible that you will not able to see the complete posterior distribution, marginalized posterior distribution of the individual parameters. So in a Bayesian approach, what we need three things. One is model, data, and cost functions. And you can see some good references are there for that. And basically, what I was talking about this under the static assumptions, your your mass radius and the pressure equation of state as a pressure as a function of density or energy as a function of density has a one-to-one correspondence. So once we have one line in MR, you can have exactly one line in the equation of state space. So once we fix the give some constraint on the mass radius domains, it will also constrain the equation of state domain. So in an equation of state derived from any assumption, any theory, we can represent or recast this equation of state in this way, or nuclear physics is more preferred, that you can expand your energy density in terms of in near saturation density, with delta is here proton fractions, and S of rho is the your symmetry energy. Now, if you take the derivative from individual and every components, all the derivatives just of the E of rho zero, the derivative first order, the second, the third, fourth, these order derivatives will represent the Q K0 is the incompressibility parameter, Q0 is the skewness, and also same thing you can get the different higher order derivatives for the symmetry energies. These all things I will refer here as a nuclear matter properties, NMPs. And so so in our model, these are the minimal number of constants we used in our Bayesian inference. These are the data we used in our Bayesian inference framework. The rho zero and E0 and all are the reasonable, well accepted, reasonable region, and pure Newton matter equation of state also had the low densities. From chiral effective field theory, we used the uncertainty 2 times because it has a very feature that it will constrain the symmetry energy. So in order to have a wider range of symmetry energy friction, we introduce the 2 times uncertainty, and for all data, the error is recorded here as a 1 sigma error, and for the maximum mass we used the different kind of, it is not maximum mass, that though we use the probability is 0 if it is mass is below 2 m solar, and probability is 1 if it is above 1 m solar. So maximum mass, there is no such kind of error, but it's a step function kind of thing. So these are the this kind is the likelihood. Normally is very the data. This data is computed, but for the maximum mass, the likelihood is not like that. Likelihood, we added the probability for. So this is our model, relativistic mean field model, and here for the Rhomazon coupling, this is we don't have any nonlinear Masonic interaction terms, but we have our couplings is density dependent, and for the Rhomazon couplings, you can see the parameter, we parameterize the couplings like this way. Exponent e to the power minus a of rho by x minus 1, and here for other sigma and omega, we parameterize. It is little bit different from the original DD2 or DDME2 kind of model, but this kind of parameter will give the equivalent things, equivalent density dependence of the sigma field or omega field. So reduce the parameter with like this way, and now we'll do the Bayesian inference. So before going to do the Bayesian inference calculation, it is good to do a prior preparation. So to know about the range of, because here our priors parameters are not the nuclear matter parameters. Parameters are the couplings. So to know the which range of couplings can give the effective. Which range of couplings can give the effective the nuclear matter parameters over a wide range. So what we did, we did a Latin hypercube sampling. It's kind of a it will do a random sampling in a hypercube with a, you can fix the number how many samples you want, and with this you can first calculate the all the star properties or the individual components of the equation of state, also the nuclear matter parameters, and you can see that your prior span is enough to perform the calculations. So in this way, we set for the prior range for all the parameters. Now, once the prior range is fixed, now it is the sampling. For the sampling, what we have done, you have used the pi multiness sampler, because there are normally widely used one sampler is called the MCMC. What MCMC does, it will do what MCMC does. It will do a Markov random sampling, but guided by posteriors distributions. But in a nested sampling, what it will do, that it will break the your posteriors into many slices and start sampling from each and every slices, and at the last it will recombine all the distribution and make a full posterior distributions. So there are not many advantages. Of the one advantage is the when you have the high dimensionality problem, then the MCMC does the better job. But you have a low dimension, but you want to see if there is multimodal things exist, then pi multinest is the best. But as we all know that in our case, neither the couplings or nuclear matter parameters so should have the multi-modes, but still it is we liked it. And now in this we did a sampling, but sampling was done by calling almost 10 to the power 5 order models, and finally the 14,000 models is selected. And with this posterior distributions, first we can see the corner plot of the this 40,000 model, the corner plot of the parameters, marginalized distribution of the parameters, the sigma, omega, and you can see that the gamma, omega and sigma, these two couplings are very correlated because of the binding energy constant applied to the data, because it constrains the sigma and omega field. That's why it's correlated. Now with this marginalized posterior distribution of the parameter space, we can do the calculation for the star properties and individual nuclear matter parameters and see how the parameters are. So before going to that, there is a in the low density nuclear low density pure Newton matter equation of state from the chiral effective field theory calculations from Hevler et al. 2013. You can see that that's N3 yellow, and this is the and the gray gray hatched region is N3 yellow, and the 2 times uncertainty shows the gray band, and this red region is our DD, the final posteriors obtained, and which is also fitted very nicely in this pure Newton matter equation of state. Now how the equation of state looks like, the equation of state also compatible with the GW 170817 constants, and here in this plot on the mass and radius, it is actually joint probability distribution of the mass and radius, and the gray region is on the constant from the GW 170817, and other the boxes are the constant from the NISER's observations. And you can see that the dense region in the mass radius is already compatible overlapped in the overlapped regions. So but the mass and radius was neither part of the feed data, but still in the present constants is I will say that the maximum mass constant is the more stringent constant rather than this present constant we have from the mass, NISER mass and radius. Now if we next we move to the different individual component of the equation of state. First here in the top plot you can see that the pressure for symmetric nuclear matter equation of state, and the gray hatched region is shown here is the data from heavy ion collision experiments, and it is slightly touching the upper side of the constants, although it is not that the those US satisfies the symmetric nuclear matter equation of states, constant from HIC. Its maximum mass giving the more than 2m solar, it is little bit difficult. There is a tension between that. And down here you can see the symmetry energy S of rho as a function of density, where you can see, and also we have plotted the constants from the isobaric analog state. And here you can see that the symmetry energy at the symmetry energy has a in the present constants for which we have used this in our inference, that symmetry energy can have that this wider span, and also the in the other side I have plotted the particle fraction or the proton fraction and the electron or muon fraction as a function of density. This also shows a wider span. Now I want to now we have show how the tidal deformities and other things looks like. Here you can see that this is the 90% confidence interval from conditional probability, not the two-dimensional joint probability distribution. Here, this is basically the probability of radius for a given mass. So let's say if you slice the y-axis, if you fix the one mass, then you will have a distribution of the radiuses. So this distribution of radiuses from that CDF, you can pick up the 90% regions. So in this region, the red region actually shows the one dimension conditional probability of the radius for each and every masses region. And right hand side also I have there is the same thing, conditional probability for lambda tidal deformity for given in different masses. And on top of that, we have from our this entire set of models, we selected few models and named as a DDB, which passes to the almost the lower limit of the 90% confidence, and other passes, one passes DDB-M, it is passes the from the middle, and other two DDB U1, U2, which and also one equation of state which gives the maximum mass around 2.48, something like that. So in our 90% confidence limit, we achieve maximum mass up to 2.48 m solars. And there are also few recent equation of states such as DDB max and DDB density dependence other LZ that gives more masses something 2.55. So this masses we have not achieved in our, this is not in our kind of a model. This is our outside the 90% confidence interval. Now this is the, here I have shown the corner plots first for the neutron star properties, where you can see the mass and the baryonic mass and speed of sound at the center of the star, and the central density, radius for 1.4 m solar, and tidal deformity for 1.4 m solars. And here radius for 1.4 m solar, our in our 90% confidence interval, 12.62 plus minus 0.55 kilometer, and for lambda 1.4 we got 453 plus minus, you can say 170. And the other side, it is then each and every nuclear matter distributions of the nuclear matter parameters, and on the corner all the 1D there are the 1D marginalized distribution for each and every 1D distribution for each and every parameters. And here you can see that although the J0, the symmetry energy at saturation density was part of the fit, so and the L0 was not part of the fit. The L0 we have got around 40 plus minus 40 plus minus 20 MeV, something order of that. And the Ksim 0 also the curvature of the symmetry energy, that is we got the minus 115 plus minus 40 MeV, and other higher orders also QSIM and JSIMs also has a wider span compared to other things. Now, so we in the present with the few saturation properties and maximum mass constraints, we have first tested that what is the possible domain of the nucleonic equation of state, and we have analysis all the individual components of the equation of states, and this all entire set of the US, also the few selected ones as I was describing about, which gives the different which passes the different regions of the 90% confidence interval are in the Genedos websites with this DOI. And this paper we have worked with Marcio and Vijay Agarwal and Constanza. Now the question is that one other calculation we have done with in collaboration with Professor B.K. Agarwal and Chiranjeev, where we have seen, let's say if you take a true model, first you can think like this way: you have many points in the MR space, so you know the exact equation of state. So in this way, we have taken, let's take a model and first generate a equation of state with a true parameter. Now you fit the equation of state with that model, and what you get, the uncertainties of the individual components, so E of rho 0 and the symmetry energy. So what we have seen, so fix a model. This is done in a Taylor expansion model, and here you can see the symmetry. Even you can fix the exactly fix the beta equilibrium equation of state, but you have a quite uncertainty on the symmetry energy. So there is something, the symmetry energy, the star properties or global properties can only fix the equation of state, but there is some other probe is needed to fix the symmetry energy at high density. Otherwise, it is very difficult to pin down the composition of the inside the neutron stars. So there are some future probes which seems to be promising, some quasi-normal mode oscillations. Among that, the F mode oscillations, first fundamental modes, which can vary from 1 to 3 kilohertz, expected to be detected in 3G detectors such as Einstein telescopes. This, but this can be, so also we have just very quickly, and so we have just initial calculations to this. You can see here that's DDB equations how lie with respect to other equation of states, and with this what we found that this with this sampled of equations with our all DDB equation, also we have done a polytropic treatment. So in over a wide range, we have seen that the F-mode frequency is very precisely correlated. There is a universal relation between F-mode frequency and radius of the stars. Coordination coefficient almost 0.999. So, but still it is, there has to be further, many investigation has to be done to need to know how it is correlated with the individual component of the equation of states. That's, thank you.